In the last class, we have started the diet and and which is just a minute. It's some problems going on. Now, diet is a general term. So, diet comes from comes from the vacuum tides, triads, tetrodes, pentodes, and depending on the number of electrodes you have. So, diode in general refers to that class of semiconductors that specifically has two electrodes. And it has specifically rectifying nonlinear characteristics, as all of you know, that the that is the current is being that is being conducted is exponentially related to the voltage across it, that is VD, and it is said to be rectifying in one direction, which means that the diode um, act as a rectifier in which that is in forward bias. It allows the current to flow, and in the other direction, that is when the reverse in the reverse bias direction, it gives a zero current. That means it is off in the other direction. So it's basically conducting in one direction and less conductive or no conductance in the other direction. So that is basically the property of the diode we have still noticed. And in case of ideal diode, what we have actually seen that there is an L-shaped curve, and which starts right at the origin, and it has no such sort of any voltage and all that, and it is can you okay, just uh, so in case of that, it has nothing but an L-shaped curve, and it is conductive in this direction. That means in the positive part of the voltage, and in the negative part, that is a non-conductive. So yes, mm, so p-n junction is basically one of the way by which we can make a diode. Yes, you can think it of as a special kind of diode. It's one of the most general procedure to make a diode. That means p and n being the two terminals, and there is one junction with it. We, just a small recap of the whole thing. Uh, just to draw a p-n junction once again, so that we could actually bring out the difference of it with the while adding another terminal, which is nothing but in case of the BJTs, that is bipolar junction transistor. Let us try to draw that one very quickly. So in case of a diode, what we had, so this is p side and this is n side, where in the p side we are doping with the acceptor impurity ions, and in the room temperature, if we assume that there is a complete ionization, then what we are left with, there is some depletion region that is soon formed as soon as this p and n junction is formed, and a current starts to flow. When the majority carriers holes from the p side will go to the n side, and the electrons in the n side, which is the majority carriers in the n side, will go towards this direction. Sorry, I just try to. So this is the scenario basically in which after the majority carriers crossing throughout this junction and the majority carrier electrons passing through this junction will leave the acceptor ions, that is positively sorry, these are the negatively charged ions. These are negatively charged ions on the left hand side, and these are the donor positively charged ions on the right hand side. And so these ions are relatively higher, as already in the previous discussions we have argued that they consist of the nucleus, electrons, protons, and are also bonded with other atoms, with the neighboring atoms with various bonding arrangements. So they are pretty tightly bonded. As a result, they cannot move, and here they are forming this depletion region, due to which any further movement of the majority carriers is restricted for the so the thing is now that now when the electron moves from the n side to the p side, it becomes the minority carrier where the electrons try to cross. Now even when this depletion region is formed, we have seen there are few hot electrons in the n side and few hot holes in the p side, which are able to cross. There are but those numbers are again very few in number. So now that electrons that moves from the n side to the p side will become a minority carrier in the p side, whereas a hole moving from the p side to the n side will become minority carrier there onto the n side, where there are pretty high chances of recombination. Now, the closer a carrier is to the junction, the higher is the chances of recombination. Now, when this hole, we have argued also again in the previous classes also, when this hole is particularly sitting and is able to cross this barrier potential and come manage to come over here, have pretty high chances of recombining, seen in a negatively charged carrier, that is electron here. So as and when it moves away from the space charge region towards the bulk region, more deeper into the semiconductor material, it has higher chances of recombination. So as a whole moves more towards as a whole moves crossing to the end junction by crossing this depletion region, what it is expected that these minority carriers are lost with respect to the distance from this barrier space charge edge towards this edge of the bulk region. Here also the same argument applies. That means when an electron passes from this side to this side, it becomes a minority carrier here, and it sees over there a large number of holes, which are just the acceptor centers, where which the electrons are finding themselves a much what can we say, there are more chances, as there are more number of holes, the number of majority carriers holes over there are much larger in comparison to this small number of minority carriers. They will have a greater probability of recombining with the holes over there, and hence their chances of being recombined and hence getting lost is increasing as and when it moves from the space charge A's towards the edge of this bulk region. This is the bulk of the semiconductor, and this is the edge of the depletion region width or the space charge region width. Why is the naming is the space charge width? We have also discussed this earlier. I think you know that as because these are actually covered with the space charges or the immobile ions or the immobile charges sitting over there. This is called the space charge region also. So one of the basic difference that we have interchangeably used these terms thermal equilibrium and steady state. So what is the basic difference between these two? When we say that a semiconductor is in thermal equilibrium, so if we can draw that again, then uh, in this condition, when the PN junction is applied no bias to it, that means no external potential is being applied to it, then the electrons and the holes crossing either side of the junction will be stopped under certain circumstances, and the circumstances is being guided by the total number of these space charge ions or the space charge acceptor ions and the donor ions that are present over there. And when this happens, when the flow of this majority carriers from p side to n side and hence from n side to p side is being stopped, we say that the p-n junction is now in equilibrium. Did you get that? When a semiconductor is in thermal equilibrium, a semiconductor is said to be in thermal equilibrium when no external induced voltage is being applied to that, and after certain point of time, when the majority carriers crossing on the either side of the junction stops its flow, on account of this, the barrier potential that is being developed on account of the space charge ions, we say that now the semiconductor has achieved a state of thermal equilibrium. Is that clear? Yes or no? Yes?
Yes, ma'am.
Okay. And then what is this now? Now we are going to apply some bias to it. And in this case, under no bias condition, what we have seen is that if this is your P and this is your N, then what we had this sort of energy band diagrams. And in that time, we have argued that as the semiconductor is in thermal equilibrium, what we have argued that the Fermi level in both the p site must line up to indicate that the state of Fermi equilibrium has been achieved, and the difference in the and where this is the EC in the p side, this is EV in the p side, and this is EF, which is common to both the P and N side. And here also, this is the EC, this is EV, and the Fermi level can be represented using just a line. And this energy band diagram now represents that it is in thermal equilibrium. So now we are now trying to apply some bias to it. So in this condition, the electric field will be pointing from this to this region, from the space charge region. That means from this direction to this region, where from plus to negative, positive to negative. And when we apply some bias over to it, then what is happening is that in the P side, we are connecting it to the most positive terminal of the battery. Yes, and inside to the most negative terminal of the battery, so that we can now argue that this is in forward bias, which in turn reduces the overall potential barrier. That is, if this is V1 and this is VBI, the overall potential barrier will reduce but V1 minus VBI, and hence, and this can be depicted here as what is that? As because the barrier potential, this amount is being lowered, what we say that this will move down, and this will move up. So this is so what is actually happening here? It the more and more hot electrons that will find its way. We have, if we can draw here a really Boltzmann approximation here, then you will see that the more and more number of electrons and holes will now be able to cross the junction and thereby form and thereby achieve what is known as the steady state. And in this steady state, what we have seen is that now the Fermi level will not be constant uh, throughout this junction, that is the P and N side. Rather, it will form a quasi Fermi level. That means the Fermi energy level will now split, and these will now form quasi levels. That means local Fermi levels are formed in both the sides, contrary to the previous cases where we have argued that the Fermi level that in thermal equilibrium, now the Fermi level is constant throughout the junction. Now, in this diet, what is seemingly the independent terminal, what is seemingly uh, the independent terminal? Can you see what is the independent terminal in this diet? In the diet, what is the independent terminal? The voltage is only the applied voltage. That means the externally applied voltage is only the independent terminal. Do you agree with that? So with this applied voltage, that is V1, the barrier potential is lowered and the thermal energy does the rest of the work. The barrier potential is lowered and the thermal energy does it all. That means the thermal energy that is lying within this majority carriers holes and majority carriers electrons over here does the rest of the work. So now we can redraw the picture once again. Let us try to draw that one.
Ma'am, can you please repeat that part of quasi Fermi level?
না কোয়াসি ফার্মি লেভেল হচ্ছে দেখো কোয়াসি ফার্মির আগে আমাদের কি একটা আর্গুমেন্ট ছিল আমাদের যে আমরা যখন থার্মাল ইকুইলিব্রিয়াম অ্যাচিভ করছি দেন উই উইল সে দ্যাট দ্য ফার্মি লেভেল ইন বোথ অফ দ্য রিজনস দ্যাট ইজ পি এন্ড দ্য এন রিজন উইল লাইন আপ মানে একটা সেম লাইন দিয়ে রিপ্রেজেন্ট করা যাবে বাট ইন কেস অফ যখনই আমরা একটা বায়াস লাগাচ্ছি তখনই কি দিস ইজ নট এট অল ইন ইকুইলিব্রিয়াম ওকে we are not at all in এখন কারা আসছো goodness okay now it is not in thermal equilibrium but now what does happens Fermi level will split means the Fermi local there will be local Fermi levels that will represent a closer view that means in case of the valence band in case of inside the Fermi level will move closer to the conduction band isn't that in that case, there will be two separate Fermi levels on each side of the junction. That means on the P side, there is one separate Fermi level which is used to designate the number of holes over there. And in the N side, there will be a separate Fermi level which will be used to designate the number of holes, electrons over there. That will lie more closer towards the conduction band. So eventually, what will happen is that these two differentiated Fermi levels or different Fermi levels as is depicted in the figure also. Let us try to draw it once again. So this is the Fermi level in this P site, which is lying closer to the valence band, and it will lie closer to the conduction band on account of this applied forward bias. Did you get that? Because now we have to accommodate in this energy band as to the number of that is the amount of forward bias voltage that is being lowered on account of this and the amount of the barrier potential this must account for the reduction in the amount of the barrier potential that is being lowered on account of this applied potential that is V1 yes so now these local Fermi levels are known as this quasi Fermi levels আমরা আগের দিন এটা একটু সামান্য ডিসকাস করেছিলাম if you could really recollect so the splitting of these Fermi levels are indicative of two phenomena one which indicates that the majority carriers are even more are facilitated to flow in either side of the junction and second is that now the total potential barrier has been reduced from VBI to V1 minus VBI. Is that clear?
Yes, ma'am.
Okay. So So what we are going to do actually that we're trying to draw the minority carrier profiles over here to actually bring out the notion of the BJT, that is bipolar junction transistor. So again, let us suppose this is the P side, and this is one acceptor and that is representative. Oh my god, problem. So there is one problem with this drawing. I'm just rubbing it. There is some problem that this always gets magnified. So once I actually join this, this goes out of control. That is one of the problem that I'm facing right now. So yes, now we are able to draw that one. So now let's say this is the depletion region width up to which this immobile ions that is extending up to, and let us suppose that this is there is one electron over here that has managed that has been once the majority carrier hole, that is the majority carrier electron in the inside, which has managed to cross the junction and come on to the p side to become a minority carrier over here. Again, let's suppose there is one hole here that has been going from this side to this side and then managed to cross the junction and coming at the space charge region H to become a minority carrier on the inside. Now, as this minority carriers, say this is Jn and this is say Jp, at the junction, as they go inside from the junction, there are more chances to recombine. So the density decreases exponentially with the distance. So what should be their profile look like? So their profile must look like this.
If they go away from the junction, their chances of recombination increases or decreases?
What is your thought about that?
Away from the junction, as in the minority carrier on the p side, the electrons are moving away from the junction, so their chance of recombination must decrease. Okay.
হ্যাঁ, কেন?
কেন কেন তা তো জানি না ম্যাম।
Why? না, একদমই নয়। Their chances of recombination increases. তার কারণ হচ্ছে the number of মানে holes actually that is residing in the p side, which is the majority carrier over there, is much more than the number of the electrons over there. So একটা ইলেকট্রন যেটা এনসাইড থেকে ক্রস করে এখানে এসেছে, সে অতগুলো হোলস ওখানে দেখতে পাচ্ছে। So the probability increases or decreases. A very common intuition if you can apply.
Increases.
Exactly, increases.
As we go away from the junction on the
Then
p
what is
side.
expected? The away from the junction onto the p side. That means here I am telling about this curve. This electron has is being is crossing from the junction, and if we are considering this electron here at the that has crossed from this junction and is just standing at the edge of the space charge region. Now, what is its probability? What is the count probability count? What is the number of of this minority carrier electrons now should be with time or with distance? What is the thought about that?
And with distance.
Either with the distance. What that should be with distance along with the time also. As soon as it crosses the junction, this majority carriers, as soon as it crosses the junction, okay, দেখতে পাচ্ছে there are far lot number of such kind of holes, that is acceptor ionic centers are there to get over there and recombine with them. তাহলে কি হবে, ওদের নাম্বার তো যত ডিস্টেন্স যাবে, যত ও কভার করবে এই দিকটায়, আরো যত যেতে থাকবে, তত কি ওদের নাম্বার, এই মাইনরিটি ক্যারিয়ার্স এর নাম্বার তত কমতে থাকবে। and that is so true,
Yes,
তাই
ma'am.
তো? Here also in this condition, these hosts actually find themselves sees as minority carriers over there, and they actually encounter much larger recombination centers, which are nothing but electrons in this case. তো যে কোনো একটার সঙ্গে ও প্রবাবিলিটি ও রিকম্বাইন করেই যাবে ইভেন্চুয়ালি, জাস্ট এট দ্য এন্ডে আসার আগে ও কোথাও না কোথাও রিকম্বাইন করেই যাবে, কারণ এরপর আছে হচ্ছে আমার মেটালিক জাংশন, দ্যাট মিনস the two long metallic wires with which it is connected to the outer world. এই মেটালিক জাংশনে ফেরত আসার আগে ও এই বাউন্ডারিতে কোনো না কোনো হোল বা ইলেকট্রনিক মানে ওই রিজিয়নের মেজরিটি ক্যারিয়ারের সঙ্গে রিকম্বাইন করবে, and that is eventually to do. Now is it clear to you? কেন রিকম্বাইন করবে, আর along with the distance or time why their concentrations should decrease like
ওইটা তো
this.
ম্যাম কনসেন্ট্রেশনটা ডিক্রিজ আমি
minority
মানলাম ম্যাম, আমি বলছি কি লেটস সে ফর ডিসটেন্স x and for distance x plus dx ম্যাম, তো x plus dx এ the chance of recombination বেশি নাকি x এ the chance of recombination বেশি, এটা 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 বলছি আমি।
মানে x plus dx এ obviously x plus dx এ, কারণ আমি 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 ধরেই নিচ্ছি যে আমি যত বাল্কের দিকে যাব তত আমার ইলেকট্রন কনসেন্ট্রেশন কিন্তু বেশি,
ওকে,
কারণ এই দিকটা যদি আমার স্পেস চার্জ রিজিয়ন থাকে which is devoid of of this ionic charges, that is immobile ionic charges, then obviously the chances are more towards x plus dx.
ওকে ম্যাম, ওকে।
So the profile of the minority carrier charge distribution, this is nothing but the profile of the minority, এটাও তাই, minority carrier distribution. Kintu, now the problem with the diode is that as this minority carriers are lost in recombination, we actually don't have anything to harness this property. Harness this property means we don't have any other terminal where we can actually collect this minority carriers to eventually produce a some sort of other nature, that is the amplifying conditions, or something RC couplings or like that. Uh, so did you understand this problem with the diode? They are just lost in recombination. Now, thus before recombination, what we want is to harness this property. So we definitely need a third terminal. You can see here that the minority carrier distribution always decreases and it goes away from the space charge region towards this end. Now, what to do? What to do actually? In this condition, we can just apply here one, we can add here one more terminal, so that just before getting recombined or being lost, they can be harnessed to some other regions. So let us try to put a third terminal first, then we'll discuss these pros and cons after that, and we'll try to resolve those factors. Okay, so if I can rub this one. Same problem. So we just want to add one terminal. Can you listen me?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Can you listen me? So just now what we have discussed is that um, uh, uh, we cannot control the output, which basically means that we really need a third terminal to separate the control from being controlled. Okay, so that problem is with the diode. So that is a problem with most of the two terminals in this device. Two terminals of the device, any device with two terminals. So that is the first thing that we actually try to do in the bipolar junction transistor. So let's see what we can do. So just if we are able to draw this one, so to facilitate the holes that come from the P side, say, and inject it onto the inside, and we are just collecting it from another inside, what should be the direction of the electric field to facilitate this process? So
from the P to the both
if
ends.
okay, let us try to draw the acceptor impurity ions over here. These are nothing but the donor ions, and here this is the acceptance. Here also this is the acceptor. Representations are all are lying in the bottom also, but we're just say giving the representations only. So this is the flow of electrons from this side to this side and eventually being collected to this side. What should be the polarity, what should be the what should be the direction of the electric field that can be applied to move these electrons from this side to this side, from that means from this side to this side. So if we can apply the voltages over here with so now do we agree with this arrangement? That means that now the N side is being connected to the most negative terminal of the battery, and the P side is being connected to the positive. Here also, this P is connected to the negative terminal of the battery, and N is connected to the most positive terminal. Now, when an electron moves, let us suppose we're starting from this terminal and going to this forward bias in this junction. In this junction, if this one is junction J1 and this one is junction J2, then you can see here that J1 is actually forward biased. Isn't that? J1 is forward biased, whereas the junction J2 is reverse biased. Then what are the conditions that are actually to pop up? One thing is that on account of this J1 being forward biased, what is expected? The electrons from the inside will move on to the P side to become minority carrier over there, and this minority carrier electrons, the minority carrier, this is the electron that will go over here and become minority carrier over there. And if this electron is able to cross this junction and finally come up to this region to become the majority carrier once again, then what will happen is that we are able to see a large amount of current from this terminal itself. We will see what will be the direction of the current later on. But now up to this, is it clear to you? What we are saying is that in the previous case, in the case of P and that, what actually we had is that once a majority carrier on account of its forward bias being injected onto the other side becomes the minority carrier over there, the number of these minority carriers will soon exponentially decrease, because of the reason is that we had no other terminal to collect it from anywhere else. So basically, we have added another controlling terminal. We have added another controlling terminal because before this electron being lost due to this recombination process, we just want to harness it at this terminal where it once again actually exploit the scope of being the majority carrier in the inside region. Is that clear to you? বাট এখানে কোনো প্রশ্ন আছে সেটা বলো, কেন আমরা থার্ড টার্মিনাল অ্যাড করলাম, এইটা নিয়ে কোনো প্রশ্ন আছে কিনা, দ্যাট ইউ ক্যান আস্ক। এটা নিয়ে কোনো কোয়েশ্চেন আছে তোমাদের? Yes, are you there? Yes?
Yes, ma'am. Question নেই।
সবাই ঘুমিয়ে পড়েছো মনে হচ্ছে।
হ্যালো।
হ্যাঁ, তোমরা কি প্রত্যেকে ঘুমিয়ে পড়েছো নাকি?
না না না
না
না,
না,
না, না,
এটা একটু
Okay. Okay, then the problem with the diet that we want to circumvent with the help of this the bipolar junction transistor. And the problem, I think, now is clear to all of you. The problem is that the minority carrier which is being lost at this position will now be recollected or collected in some other region, so that this property can be harnessed to actually use in some other applications like amplifying and all that. So the problem with this diet can be circumvent using a bipolar junction transistor, but the thing is that there are several conditions imposed on it before actually we can harness this minority carrier, which is of utmost importance in this case, before actually recombining with any of the holes, which is the majority carrier over here, and finally come up to this region. So the problem is clear to you. Now we have to make some arrangements so that this minority carrier in this p-type region is not lost, and we can collect this one onto this end region. So one thing is clear, that on account of this electron to reach on this side, to reach to this side, what we have to do is that we have to forward bias this junction, that is junction J1, and we have to reverse bias this junction. You can see here both of both of these mechanisms that is shown here in this biasing arrangement will facilitate this process of going the majority carriers from this region over to this region. Do we agree with this? So if you agree with this, then we can go on to several other aspects. Just before that, we'll give name to each of them. So as because this is the region
ম্যাম
where
যদি
হ্যাঁ,
আমি যদি
বলো।
J2 কেও যদি আমরা ফরওয়ার্ড বায়াস করতাম তাহলে কি যেতে পারতো না ওই মাইনরিটি ক্যারিয়ারটা ওই সাইডে?
তোমার
আটকে
ইন্টুইশন
যেত
কি
তো,
বলে?
পিতে
হ্যাঁ?
আটকে যেত, পিতে আটকে যেত।
আচ্ছা
পিতে
আচ্ছা।
দেখো একটা জিনিস দেখো, if electron has to move from, if an electron has to move from this side to this side, what polarity in this region should facilitate this process? Obviously positive polarity
Yes,
to
ma'am.
get collected at this region, really.
Yes, ma'am.
So if you have put it a forward bias over here, that means inside connected to the most negative terminal, that must not facilitate this process.
Yes. Okay. Yes, ma'am.
Okay, if you accept these conditions, then just giving the names over here. So this terminal is called the emitter terminal. This is called the collector terminal. As the nomenclature goes, terms is actually named for the emitter, from which actually the flow starts in particularly in one direction. The directivity starts from the emitter region, so it's emitter. Next, we have got another terminal which is collector, which is nothing but which is nothing but the output terminal, as well as you can call it as the collector terminal, from which we can arrive at a significant amount of current. So this is the collector terminal, and this terminal is known as the base. So why it is base? Let's go to the history, then it will be clear to you. Now, in probably 1947, first just a few things that you have to know. During 1904 to 1947, on October 23, probably 1947, this electronics industry has to experience the advent of a completely new direction of interest and development, and that too with the aid of this bipolar junction transistor. It was on the afternoon of this day, that is 23rd December 1947, J. Brittain and John Bardeen demonstrated this amplifying action of the first transistor, that is the one first, which is the bipolar junction transistor at the Bell Telephone Laboratories. Now, the actual transistor which was first demonstrated during that time was nothing but a point contact transistor. Was nothing but a point contact transistor. Let us uh, try to draw that one. Uh, it has a large base. It has a large base, and it has some sort of a triangular. Uh, this was actually the a non-conductive material, and above it there was a coating of a conductive material, maybe some actually this is some conductive material along, which is actually embedded after this non-conductive material. Now there is one small cut that is being done over here, so that and this triangular shaped thing is being put it over here, and this side has become at the emitter. This is the collector, and this is the base, and this one was a gigantic base. This one was a gigantic base, and hence that is actually because this triangular shaped emitter and collector regions were used to mount over onto the base. That base was actually fixed or mounted, and hence we call it as base. From there, the base terminal base has coined its name. But now the problem is that this base was so huge that most of the things that is being emitted from the emitter itself, that is being recombined at the base region, and hence we are not getting an efficient bipolar junction transistor now that we are getting. This was a point contact transistor. So this original transistor, this was actually a point contact transistor that was first demonstrated, and that's how the base has coined its name. So this was a
Ma'am,
point.
base stuff conductive.
Yes, base was conductive, and a base was actually made of a different doping type than that of emitter and collector. So the
বাট এমিটার
advantages of
কালেক্টরে ডোপিং, এমিটার কালেক্টরে ডোপিং সেম ছিল তখন?
হ্যাঁ একদম emitter emitter আর collector এর doping same ছিল, but now there are
এখন তো
some
ডিফারেন্ট নেওয়া হয়,
variations. হ্যাঁ
এখন তো ডিফারেন্ট নেওয়া হয় তিনটেরই।
হ্যাঁ তিনটে ডিফারেন্ট নেওয়া হয়, এবং কেন নেওয়া হয় সেগুলো আমরা ধীরে ধীরে আসছি একটার পর একটা। Okay, no, so why the name base? So now it's clear to you. So we are trying to actually so when this majority minority carriers like this are lost, so when this minority carriers are lost, we have lost basically the leverage. We want to use the carriers and collect them to another region. We can use them suitably without significant reduction in their numbers. Now the problem statement is clear to you, that is the minority carriers in the base region, if they are lost, Now, if they are lost, then we are actually losing the leverage. So our target is to collect them to another terminal where you can use them so that their numbers are not reduced very much, and we can get a significant amount of current where we can actually manipulate them. So let us try to draw the bipolar junction transistor once again. I'm intentionally putting a gap here because I am facing too much of the problems while joining these two things. It always gets magnified. So I'm taking an NPN transistor. Yeah, the same logic applies for the PNP transistor also, that you can also go through it. Now, we are again giving some biasing arrangements as because we have already acquainted with the fact that the junction J1 needs to be forward biased, and junction J2, which is nothing but this one. This is J1 and this is J2, and this needs to be reverse biased. So here is our complete picture. Now let us try to draw the energy band diagram in this case. So this is N side, and this side is the P side, and we are drawing it for the up to this N to P. So this is N, this is P, and on account of this for and this is nothing but base to emitter voltage, as because this voltage is being applied across the base to emitter junction. Hence it is this is emitter, this is base, and this is collector, and hence this name is VCB. Is that clear to you? So without giving V1 and V2, we will specifically call their names in terms of its names of their junctions. So this voltage is being applied at the base to emitter junction, so it's VBE, and this voltage is being applied at the collector to emitter junction, so it's VCB basically. So now the function of this VBE is what? To reduce
To give forward
to, re-
bias.
to reduce the potential barrier from N side to P side, so that now the condition is this, and now the condition is this. Now the condition is this. So that now the overall potential is being reduced, which was VBI before, which is nothing but this VBI, and this one is nothing but VBI minus VBE. So VB is actually facilitating the flow of the majority carriers holes, that is electrons, from the N side to P side, and also from P side to N side.
And ওটা VBE minus VBI হবে না?
Exactly, VBE minus VBI minus VBE I have written because now যে হ্যাঁ VBE minus VBI ও লিখতে পারো as is, এটার মধ্যে কোনো ডিফারেন্স নেই, কারণ একটা সময় হবে যখন VBE VBI এর থেকে বেশি, only in that case this forward bias thing, that is the flow of the majority carriers will happen. Okay, so VBE minus VBI, you can also write it like this, VBE minus VBI. Karan VBE actually we have that leverage to increase it like anything else. So you can write it VBE minus VI. So it ultimately what it does is the lowering of the potential barrier across the junction, and to facilitate the flow of the majority carriers from either side of the junction. Now, what type of voltage polarity will facilitate this process that we have seen? That is the forward bias in J1 and reverse bias in J2. Now, if we have really a reverse bias at the junction J2, আমরা N আর P টা কিন্তু ড্র করতে পেরেছি। Then what about the rest? আমাদের তো আরেকটা জাংশন আছে, that is N. So what will it look like? As because we are actually in doing the reverse bias over here, what we are actually doing, we are actually lowering the potential to a larger extent, so that we will now have a much steeper slope like this. Thus the electrons will be collected at the collector in this side, that is on the N side, that is on this side, at much steeper slope. But what is the first order effect that is doing this? What is the first order? First order effect means the effect that is the most influential one. Which is the most influential in this case? The thermal energy of the electrons and the holes, the thermal energy of the carriers. Look, we have already applied some bias over to here and over to here. That is already facilitating the process of the flow of the majority carriers on either side of the junction, and thermal energy does the rest of the work. As and when we lower the potential, what we are actually doing, the what actually let it move on the either side, the thermal energy only. So on account of this thermal energy, it will move downwards like anything. Now, if we want to collect most of the minority carriers onto the collector region, what kind of base region do we need? Now, let's think about it. What kind of base region do we actually need to facilitate the maximum flow of the emitter carriers towards the collector region? What kind of base region should we have? Any thought?
Lightly doped.
Yes, that should be lightly doped, but
And it should be small also, so that
lightly doped in comparison to what? It should be lightly doped in comparison to what?
the first N, the
Emitter. Emitter.
emitter. Yeah.
Let's think of the first order influence. That means the thing that will be most facilitating this process of maximization of the emitter current to the collector current that can be transformed into the collector current. What is the main thing? That is the first order. The base needs to be thin. Do you agree? As the base becomes thin, more and more electrons will pass on to the junction itself. More and more majority carrier electrons will pass to the junction, cross the junction J2, and will find themselves in the region where they will be the majority carriers again. That means on the N side. So as they are more and more thin, it is more chances that will move quickly onto the other side of the junction. This will move quickly onto the other side of the junction. Now, the second order influence, what one of you have already mentioned, what should be the distribution of my minority charge carrier if the base is thin? Now, I have considered that one condition is base is to be thin. Base to be thin. Now, my second question, if condition 1 exists, that is base is thin, what should be the distribution of these minority carriers, which is the electrons from the N side if the base is thin. What should be that? ম্যাগনেটিক ক্যারিয়ারের প্রোফাইল আমার কিরকম হতে হবে? একটা এরকম প্রোফাইল, একটা স্ট্রেট লাইন এরকম প্রোফাইল, না এইরকম প্রোফাইল? কোনটা, প্রোফাইল 1 or 2? Which one?
1. It should be 1. The straight line one.
Is it really?
Ma'am, it will be the second one. It will decay, but we want to maximize the current. So we want to make it somehow like a straight line one.
Ma'am, I think it will be the second one, ma'am.
Yes, that if you can recollect from the earlier classes also, that we have mentioned there that the minority charge carriers, that means the majority carriers that cross from this junction and find it over there, we have maximum distribution over here. And as and when it crosses the distance over through time, it will have an exponential decay. Now, why I have approximated it as a straight line instead of an exponential decay? As the electron passes through it, it has more and more chances to be present on the left, and when they are going to that side, it would get to the collector region. It's true, but the thing is that in this meantime, that is in the base region, where we have a number of holes in this region, the chances of the electrons that is going to recombine with the holes over there is maximizing, because as and when we go from this junction towards this bulk region, we will see more holes here, more probabilities to get recombined, so that if the probability of recombination or the number of finding this minority carrier, if this one is, if this is this height, then probably towards this end it will obviously decay along with time and along with distance.
Ma'am, your pointer is
That
not
we have
visible.
already argued. But now,
Ma'am, your pointer is not visible, ma'am.
now is it visible? এখনো
ম্যাম
দেখা
অ্যাকচুয়ালি
যাচ্ছে?
কোন জাংশনটা বলছেন ওই পোর্শনটা ঠিক বোঝা যাচ্ছে না, পয়েন্টারটা এত ছোট।
এই যে এই পোর্শন, আচ্ছা আমি কি একটা মোটা পেন নেব তাহলে? এবার বোঝা যাচ্ছে?
হ্যাঁ ম্যাম, হ্যাঁ
আমি ডিফারেন্ট কালার
হ্যাঁ হ্যাঁ
করেছি।
হ্যাঁ হ্যাঁ।
Okay, now the majority carriers, which is nothing but electrons, the probability of finding an electron in this region is more compared to this region, as because now and the number of minority carriers, which is the electron in this case, will decrease through the time and distance, as because you will find more and more recombination centers over here, that is the holes over here. So the thing is that the minority carrier distribution, that is the minority charge carriers, will decrease from this position, from this, if this is at this height, now getting lower. So from the current density profile, from the first, that is from this figure, if the PN junction is very short, if the PN region is very short, if this region is very short, this region that is marked pink is very short, then the decay can be approximated as a straight line. We are considering an approximated, we were actually considering an approximated result when we were actually considering long PN junction. Do you remember that?
Yes, ma'am.
But when this junction is short, but when this PN junction, the bulk region is short, we can approximate as a single straight line. When long PN junction, we approximate that as a, and when we can actually look, anything which has its probability directly proportional to its number at that time can be approximated as an exponential. So this also, in this case, this is also true. So at this point, the number is the number is directly proportional to the probability of its of the number of the holes here also. So what is that? So we can actually approximate is an exponential, but in case of a short p-n junction, that means when the region is very short, then we can approximate as a straight line instead of an exponential. That means it has a linear relationship with this. So more narrow. So the base region being more narrow, more and more narrower this base region. So if this is your base region and this is your emitter and collector, once this region becomes more and more narrow, more electrons get collected at the gate terminal without having its number reduced on account of this recombination. যত সরু হবে বেস রিজিয়নটা যত সরু হবে ওর তত চান্সেসটা কমে আসবে টু গেট রিকম্বাইন বোঝা গেল তাহলে মোর এন্ড মোর ইলেকট্রনস ফ্রম দ্য ইলেকট্রন emitter terminal will get on to the will reach to the collector terminal. Now IC can be in this condition can be approximated as IS e to the power VBE by VT, and VT is what? KT by Q. Obviously is there are some other factors also on which is depends, because is also depends on the doping concentration of the base region, the cross sectional area of the base region. There are several other dependent factors of this is, but the most important factor is that now we have this collector terminal current, that is a collector current that is dependent on the base to emitter voltage. You can see here that if we increase this VBE to a large extent, to a very small extent, then the IC will increase exponentially to anything like any order. That actually makes that's producing a very high transconductance of this BJT. That makes BJT actually very bulky and beefy device in the end. Now, so the one of the very important factor that determines this collector current is nothing but the thermal energy, and this thermal because we have also inserted this VT term, which reminds of the thing that this is a thermal device. It is dependent on temperature, and VTE, if we put all the things over here, it is nothing but 25.8 millivolts. So if we put it over here, and you can plug here the any VBE, and we'll see that there is an exponential rise in the collector current. So basically what that dictates, it basically dictates that it is a voltage controlled current device. The output is one, that is the current, and the controlling terminal is the controlling parameter is the voltage across the base to emitter. So it is nothing but a voltage control current device. Question often comes from this also, which means that a small change in VBE leads to a large change in the current IC. Now let us try to draw the current IC versus VBE curve, as because we have already given this notation here. IC is equal to IS e to the power VBE divided by VT. So I'll try to draw that one. So like this is our IC, that is a collector current, that means the output current. This is the controlled parameter, and this is what the controlling parameter. This is the parameter which is controlling this current. So basically the controlling terminal and the control terminal are different. Can you see that? The controlling terminal is nothing but VBE, base to emitter junction, from which we are being controlling the collector current, and the controlled terminal is nothing but the IC, that is the collector terminal. And this is nothing but, if we can extrapolate it, it is VBE and VBE is given by VT ln IC by IS. Now, can we make this base incredibly thin? So we have argued that one of the possible option for us is to make the base thin in order to collect maximum of the current from the collector terminal. So now my question is that can we make this base incredibly thin to facilitate the injection of the minority carriers onto the collector region? So can we make this base thin and thin more and more thin? Can we
No,
make
ma'am.
this?
Like if we
Why?
make more thin, then the junction one's electric field will interact with the junction two's electric field, and if that happens, then it won't be able to the response won't be able to pass.
And J1 and J2 will overlap.
Yes, yes. We cannot do this. You have actually pointed this very true. Because as we do this, the depletion regions, if this is E, this is B, and this is C, and if we are now making a B very small, very thin actually, then the depletion regions will hit each other. One that is being shared with this and one that is being shared with this. Is that clear? So in the E side, there is one acceptor ions, and in the B side, here, 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 and here. And in this side again, we have this. So actually, I have done NPN, no? So this is plus and this is minus. So I have done a mistake over here. E, B, and C, and this depletions regions will hit. So this will hit onto this onto the depletion region that is formed on account of the BC region being reverse biased. Okay, the region BC being reverse biased, that will hit with the depletion region that is formed across the BE region. And the separation actually what will happen then? If these two regions hit each other, what will happen? Now again we can draw this. Now this is the condition when we have taken a considerably thick base width region, but now I am arguing that the base region is incredibly thin. What will happen? Actually, we are lowering the potential once again. If we are again making the base thinner and thinner, and we are going on increasing the VBE, what will happen is that this will be lowered. Once again, this is lowered. This is lowered. This is again lowered, and this is lowered. In this case also, lowering this, lowering again more this, again lowering this, we will achieve to a condition when we will see that no such junction is actually now possible. That means we are there. That means the separation of this output port, this is output port, and this one was our input port. Now this separation is now actually not available. Did you agree with this? Eventually, we've actually lost our leverage when making these two junctions and three terminals. Can you get that? আমরা যেই এই দুটো আমরা এই বেসকে থিন করতে করতে এমন একটা জায়গাতে নিয়ে এলাম, বেসিক্যালি এই পয়েন্ট অফ টাইম থেকে আমি কিন্তু আর আমাদের এই সেকেন্ড টার্মিনালকে কিন্তু লুজ করলাম। That means now what? We're actually now left with a two terminal device. And now what we can say is the controlling and the controlled output port, that is the controlling and the controlled port. This is the controlled port, this is the controlling port. These two ports now merge. You can see these two now merge. And this effect is known as punch through effect. This is a specific name, that is punch through. So not that they will hit each other, but the thing is that that will turn a BJT into a diode again. That is this region, making the base incredibly thin, will transform a BJT into a diode once again, and we have lost actually the leverage of making the third terminal. So
What
now
was the
my
effect?
another question. Huh?
And the effect, what was the effect's name that the controlling and control ports get merged?
Hmm.
And what
It
was
is
the
it
effect
is
name?
getting.
And you said a name, na? That effect, that is called a particular effect.
হ্যাঁ, যখনই এরা মার্চ করলো, দ্যাট মিন্স হ্যাঁ, that is punch through. That is called punch through. This phenomenon
Okay,
is
ma'am.
known as punch through when the base is very, very thin. But what if we want to make the base thin without the depletion? Now I have understand the problem that base should not be made that very thin that when these two depletion regions will merge with each other. Now, if we are able to make a base heat each other, then what another thing we can actually do to make the emitter current go past towards the collector current to gain the maximum efficiency. নাও দেখো আমাদের প্রথম প্রবলেম হচ্ছে কিন্তু এমিটার থেকে যেভাবেই হোক ইলেকট্রনকে আমাকে কালেক্টর টার্মিনালে নিয়ে যেতে হবে। ফর দ্যাট আমার ইস্যুস গুলো আমরা এক এক বেস থিন করা যাবে, কিন্তু একটা সময় পর সেটা থিন করা যাবে না, কারণ that will make again that thing that is the punch through effect that will come over and will make actually transform this BJT into a diode again. So that is not helpful. কিন্তু বেস টার্মিনাল আমরা থিন করলাম এতটুকুই যেখান থেকে আমার এই পাঞ্চ থ্রু এফেক্টটা আসবে না। বাট what is the another thing that we have to really bother about to actually make this emitter electrons, that is the electrons from the emitter to reach to the collector terminal. Now another option is to, in doing that, is to increase the doping concentration of the base, and that we can do. Do you agree with me? We can now, so the third option. So we have already discussed two issues. So our third option is, increase doping of base. আবার ছোট্ট করে ড্র করে ফেলি NPN। নাও আমি বললাম কি আমরা বেসে ডোপিং ইনক্রিজ করতে চাচ্ছি। we want to make the we want to increase the doping of the base so that maximum of the current, that is the maximum of the electrons can reach over to that collector region. So if we want to shrink the depletion region on both the side, now what happens is that আমি কি বললাম, আমি ডোপিং, হ্যাঁ
ম্যাম যদি আমরা ডোপিং ইনক্রিজ করি তাহলে চান্সেস অফ রিকম্বিনেশন তো বেড়ে যাবে না?
yes, I am discussing that now. I'm also discussing that now. Have some patience. So I am what we have saying that we have already doped the emitter with the highest doping, that is N plus plus and P plus, and this one, this is the collector side, this is base side, and this is emitter side. So in the emitter side we have the largest doping, intermediate doping level is the base side, and in the collector side this is the lowest doping side. So as we increase the doping, what happens is that more and more depletion region will extends towards what? Towards the low doped region in this region. Side compared to P plus. So in this case, what happens? This will have larger depletion width compared to this side. So if I want to shrink the depletion region on both the sides with the same ratio, what should we do that? We increase the doping concentration by an
Hello.
equal amount. Now, if we finally land up in making a base thin without hitting each other, what problems do we encounter? Now, some of the VBE voltage drop, let us try to connect it again. This is VBE, which is forward biased. This is VBE and this is VCB. Now, some of the voltage drop will be across the series resistance. You must have noted that with the increase in depletion region width, there is one resistance associated with it. We have drawn this in the context of when we have actually tried to derive the increased resistance on account of the increase in resistance when we are actually reverse biasing the PN junction diode. And in that case, what we actually have and we where we have seen that with the increase in the depletion region width, there will be the increase in the resistance if these are invisible, but still we have to consider it because these are the series resistance that will be varied on account of this various potentials that is being applied. Once you increase this voltage, this will be lowered. Once you decrease this voltage, this will be this will be lowered. So some of those voltage drops, that is the VBE, will be across this series resistance. That means R1 plus R2. So some of the voltage drop of VBE will be across this one. Thus, some portion of VBE is lost across this, which is a loss. Thus, we have to increase the doping. If we can make a transistor now with a base not very thin, not also very wide, what another aspect now we encounter? With the increase in VB, the potential barrier is lowered. With the increase in VB, the potential barrier here on this side will be lowered. Thus, the whole bunch of new electrons can pass onto the P region. Also, a whole bunch of new holes can pass into the N region in this site. But note that this is not a good thing because now holes after going to this N site are lost due to recombination. And this is the emitter injection efficiency loss. Now, increase in VB, what are the effects that we are going to encounter? We cannot increase the VB also incredibly, as because when we increase VB, as and when these electrons pass to the base region, here also the holes, which are the majority carriers in the base region, will pass to the emitter region. Now, what a emitter injection efficiency parameter, which is nothing but gamma, and it is nothing but INE divided by INE plus IPE. So IP is nothing but this parameter, and INE is this one. That one is the in the emitter side, the number of the majority carriers, that is the electrons, which is in the emitter side, that has crossed to the p side, and pe is the number of the holes that is going from base to the emitter, that we also have to take into account in this case, because when these holes find its way to the emitter, these are lost on account of the recombination. Do you agree with this? তাহলে emitter injection efficiency, which is nothing but gamma, is nothing but the total number of carriers that is being injected divided by the total number of electrons plus the total number of holes, because this is a contributing factor to the number of holes that is going from this side to this side, as because some of the electrons are also lost on account of these holes being falling into those electrons. Do you get that? তাহলে বেশি আমরা যদি বেস সাইডেরটা বেশি বাড়াতে শুরু করি, then what will happen? এখানে এই অবধি কোনো কোয়েশ্চেন আছে সেটা বলো।
ম্যাম গামারটা কি জিনিস একবার একটু বলুন।
গামা হচ্ছে এমিটার ইনজেকশন এফিসিয়েন্সি। এমিটার মানে how well an emitter can inject its majority carrier electrons to the either side of the junction. Emitter injection efficiency. And emitter injection efficiency তে দেখো দুটো প্যারামিটার আছে, একটা হচ্ছে the majority carrier electrons, the majority carrier in the emitter side divided by the majority carrier in the electron emitter side plus that is being pushed on from the base side to the emitter side. Our emitter side base to emitter voltage ততটাই দিতে হবে, that means we have to circumvent for this loss. Actually we have to replenish this loss. We have to increase the VB up to such an extent so that we can actually replenish this loss of recombination of these holes, that is the holes from this side to this side going over here and recombining with one of the electrons here and getting lost. Do you get that? এইটার জন্য আমাদের VB কে বাড়াতে থাকতে হবে, but how much? VB কে কতক্ষণ বাড়াবো? যতক্ষণ এই P কে আমার এই P এর জন্য এই লসটাকে আমায় রিপ্লেনিশ করে যেতে হবে। So that basically dictates or guides the emitter injection efficiency. And in that course of time, there is one generation, that is NEE, and there is one loss or the recombination, that is IPE. And in the ideal case, what we want is that this should be zero, so that gamma is equal to 1. That means this IPE should be 0, so that gamma is 1, which is a maximum efficiency that is observed in this case. Now, how to maximize this? So if our target is to maximize this emitter injection efficiency, how to achieve this process? Now, one of the very possible way that I can remind is that to give a larger doping at this site. That is why we have given here N++. So give a larger doping at the emitter side so that the loss that is done due to the minority carriers from base to the emitter region can be replenished on account of this larger majority carrier at the emitter site. Do you get that?
ম্যাম লসটা তো হোলের হলো ম্যাম, তো আমি ইলেকট্রনকে বাড়িয়ে আমার কি লাভ হচ্ছে?
এই লসটাকে আমরা কিছুটা IPE মানে এই লসটা অনেক মানে this majority carriers are much larger compared to the minority carriers, so that we can actually the number of electrons that will be crossing from this side to this side this junction, and hence finding this junction will be much more. দেখো তুমি তুমি প্রচুর তুমি তোমার কাছে এখন প্রচুর জিনিস আছে, তোমার কাছে ধরো প্রচুর জিনিস আছে। এবার যদি তোমার কাছে সমুদ্র আছে, ধরো ইউ হ্যাভ এ সি, তোমার থেকে যদি এক বিন্দু জল কেউ নিয়ে নেয়, ইউ ডোন্ট হ্যাভ সাচ এ গ্রেট এফেক্ট অন ইউ। কথায় আছে একটা, সমুদ্র থেকে এক বিন্দু জল নিলে কিছু হয় না, তাই তো?
Yes, ma'am.
So now এই সমুদ্রের জল মানে this sea of electrons will actually make up the collector current, a large collector current. So I am just trying to deduce the possibilities so that we can actually come up to the design what we are trying to do. That means what should be the actual design of a BJT or bipolar junction transistor so that we can make a helpful device in the end.
Ma'am, how did you say that we can increase the emitter injection efficiency?
By actually, if we can make up for this loss, IPE is much smaller compared to that means
Okay,
IPE is tends to 0. If in that will only happen when the base junction base is being doped with much larger impurity compared to the emitter region. Okay.
Yes,
And that is only possible, and this emitter injection efficiency in that case will reach to its maximum value, that is 1. Now how there is another possible way in doing this. Can anybody tell? So this injection efficiency, the main factor of its loss is nothing but the backward injection of holes. This is nothing but backward injection of holes. Injection of holes. So the one of the determining factors for this lowering of this emitter injection efficiency is the backward injection of holes. So as the holes from the p side comes to the n side, some of the electrons are lost when the holes recombine with the electrons. This is not only the reason for the reduction in the number of electrons. The electrons which are traveling to the base are also lost due to recombination with the holes here. দেখো এখানে আরো একটা রিজন আছে যার জন্য কিন্তু এই যত কটা নাম্বার অফ ইলেকট্রনস পৌঁছচ্ছে কালেক্টরে, এখানে লসের কিন্তু আরো একটা কারণ আছে, সেটা কিন্তু তোমরা কেউ বলছো না। একটা রিজন যদি হয় এই ব্যাকওয়ার্ড ইনজেকশন, এই যে ব্যাকওয়ার্ড যে ইনজেকশন হচ্ছে ফ্রম দিস সাইড টু দিস সাইড and gain recombined here with some of the electrons over here and reducing the total number of electron concentration in this emitter region. আর সঙ্গে আরেকটাও রিজন হচ্ছে one of the another most important reason, এই যে ইলেকট্রন বেসে যাচ্ছে and some of these electrons are again recombining it over here. There are two possible reasons for the electrons in the emitter region to get decreased. Is that clear? One is the forward injection to the base region and another is the backward injection of holes. And these are two different nomenclatures. Up to this, it is clear to all of you? না থাকলে আমাকে বলো। I think it's clear. So the loss mechanism. So now talking about the loss mechanism, one is the and for measuring this mechanism, there is one base transport factor which is nothing but alpha T is given by INC divided by INE. This is nothing but the number of electrons. What is INC? What is INC?
Number of collector electrons.
Number of electrons that
The collector.
finally reach
And
to the collector. যে কটা আমরা কালেক্টরে ফাইনালি পাচ্ছি,
Yes,
that
ma'am.
finally reach to the collector. সবকিছু লস টস হওয়ার পর, যেখানে যা রিকম্বিনেশন হওয়ার পর যে কটা আমরা ফাইনালি কালেক্টরে পাচ্ছি, দ্যাট ইজ সিম্পলি আইএনসি। আর আইএনইটা কি?
এমিটার থেকে কটা বের হচ্ছে।
আর এমিটার থেকে কটা বের হচ্ছে। আর এই লস ফ্যাক্টর, দ্যাট ইজ বেস ট্রান্সফার ফ্যাক্টর, হচ্ছে নাথিং বাট দ্য লস। এই আলফা টিটা হচ্ছে লস। The total number of electrons that we are started off with, electrons at emitter that we started off with. তাহলে লস মেকানিজম কটা কটা আমাকে একজন বলো তো। নাম্বার অফ কালেক্টরস, নাম্বার অফ ইলেকট্রনস, একজন আমাকে বলো লস মেকানিজম কি কি। নাম্বার অফ ইলেকট্রনস দ্যাট reaches collector. বলতে পারবে কি লস মেকানিজম কটা কটা? Okay, now going on to this, the final diagram of this, and two important factors that alpha we have
Ma'am.
already. Yes.
Ma'am, we were talking about increasing the dope of the base. Ma'am, ওখান থেকে এখানে কি করে চলে এলাম?
Yes, আমরা বেসের ডোপিং বাড়াতে কেন চাইছিলাম? বেসের ডোপিং আমরা বাড়াতে কেন চাইছিলাম? Let us discuss that.
ম্যাম এই লসটাকে ম্যাম ওভারকাম করার জন্য।
কারণ না, হ্যাঁ, বেসের ডোপিং আমরা বাড়াতে কেন চাইছিলাম? কারণ আমরা বেসকে একটা সময় পর বেশি থিন করতে পারছি না, নালে তো থিন করলে আমার কাজটা মিটে যাচ্ছিল, তাই তো?
Yes,
বেস একটা আপ টু এ সার্টেন লিমিটের পর আমরা কিন্তু বেস থিন করতে পারছি না। দেখো আমাদের যদি ফাইনাল প্রোফাইলটা আমরা দেখি, সেখানে আমরা একটা জিনিস দেখতে পাবো, তোমাদের অলরেডি ড্র করেওছি, আরেকবার আমি এটা ড্র করছি। দেখো প্রোফাইলটা যদি আমরা ড্র করি, তাহলে আমরা দেখতে পাবো এটা দেখে কিছু বোঝা যাচ্ছে? আচ্ছা, এমিটারটা কিন্তু আরেকটু চওড়া হবে আর কি, ঠিক আছে? আচ্ছা, আমি একটু ভালো, this is concentration and this is let's suppose with distance. So this is emitter, this is base and this is collector. Emitter এর সবথেকে বেশি ডোপিং, কিন্তু এর উইডথ হচ্ছে বেস আর কালেক্টরের মাঝে। দেখো উইডথটা, এমিটার উইডথটা হচ্ছে বেস আর এমিটারের মাঝখানে। বেসের ডোপিং হচ্ছে মাঝামাঝি, ইন্টারমিডিয়েট লেভেল অফ ডোপিং, but is width is the smallest width, and collector is the smallest doping but width is the largest. Did you notice that? এবার বেসকে কি আমরা ইনক্রেডিবলি থিন করতে পারছি না। সো দ্যাট বেসকে কেন ইনক্রেডিবলি থিন করার কথা বলেছিলাম? যাতে আমার ম্যাক্সিমাম অফ দ্য এমিটারের ইলেকট্রনগুলো কালেক্টরে সোজাসুজি পৌঁছে যায়। থিন করেছি কেন, বেস থিন করেছি কেন? যাতে আমরা তাড়াতাড়ি করে আমাদের এমিটার পাস অন করে যায় বেস থেকে উইদাউট falling into the base recombination centers and pass to the collector region, giving considerable amount of collector current. That was our motto in making base thin. but we cannot make the base very thin. The reason is because that in making the base thin, the collector regions heat each other. The depletion regions heat each other, and in doing so, what we have we have actually lost the leverage of a terminal that was previously a three terminal device with two junctions. Now it has become a two terminal device with a one junction. আমরা দেখেছি সেটা এনার্জি ব্যান্ড ডায়াগ্রাম থেকে লোয়ার হতে হতে what will happen is that we have transformed a three terminal device into a two terminal. এটা আমাদের টার্গেট নয়। তাহলে আমরা বেসকে incredibly thin করতে পারছি না। Then what we will do, we will increase the base concentration, base impurity concentration to an extent that is higher than that of the collector region. তাতে কি হবে, what will happen is that as because base is again is given a smaller doping with respect to the emitter region, in lieu of that, what will happen, smaller number of this base electron, that is the base holes, which are now the minority carriers in the electrons, will recombine, and the loss of the electrons in that case in the emitter region will be less on account of this backward injection of the holes onto the emitter side. Is that so? And in that case, we can achieve our both ends met, as because now we can actually make this loss mechanism as far as less as possible, and to make a room for the electrons in the emitter side to cross maximally to the collector side. দেখো আমাদের প্রবলেমস গুলো কি কি ছিল, সেখান থেকে আমরা কি কি ভাবে সেগুলোকে আমরা মিটিগেট করতে পারছি, দ্যাট উই হ্যাভ ট্রাই টু সর্ট ইট আউট। বেসকে আমরা হঠাৎ বাড়াতে চাইলাম কেন, বেসের ডোপিং কনসেন্ট্রেশন আমরা বাড়াতে চাইলাম কেন, সো দ্যাট compared to the collector region, what happens, যাতে রিকম্বিনেশন সেন্টারস গুলো বেসে বেশি থাকে, and in that case বেসকে মডারেটলি থিন করে যেটা হবে, আমাদের এমিটারের সাইড থেকে যত মেজরিটি ক্যারিয়ার্স কালেক্টরে যেতে চাচ্ছে, they can actually go, but again base doping should be kept lower than that of the emitter terminal, as because there we should not get significant loss in the number of the majority carriers in the electrons. So that is the reason by which we can deduce that in the emitter region, the doping concentration is the highest, base is being the intermediate doping level, and collector is the least doping concentration. Now another thing by which we can maximize this collector, because in the end we have to bring out the concept by which we can maximize this injection efficiency. Until and unless we are able to do that, we cannot use it to amplify a device, to make a device amplify something that we are going to amplify. In this case, you can see that if alpha is actually greater than 1, then we can actually amplify this emitter to that is the collector current. If you really look at this picture, then if our target is to amplify, to work a BJT as an amplifier, then we must make some arrangements so that in the end at least the current that is being sent by the emitter terminal can be received at the collector terminal, but not less than that. Now it is clear to you. So another way of doing this is that we can use a different base material. Henceforth, we have if we have started off with silicon, then we are making emitter based collector all with silicon. But in case of the base region, we can actually dope with some different material, say silicon germanium alloy, and for that, and if we can make this one, we are we can actually have to have a narrow band gap, and this is also known as heterojunction transistor. So that can also give up our a band gap which is slower. And in case of slower band gap, what is it? So that the transport mechanism is facilitated. We can so another possible way by which we can do it is um, just introduced just introduce a material of different thing, that is say silicon germanium alloy. Germanium also has a narrow band gap. Germanium also has a narrow band gap, maybe possibly 0.3 volt electron volt. So you can also use that one. And this is heterojunction. This actually leads to heterojunction bipolar transistor. That is also read in some context. But now the thing is that if we really have to harness this property, that is the majority carriers holes in this side going to this side, and you have to really harness this property, we have to attach another p type over here, so to make a pn sort of thing, that is read in some another topic maybe probably. So this is the thing why we were actually trying to derive the conditions on which the BGTs will work the best. So deriving it in a more pictorial manner, let's try to draw the final current as well as the loss mechanisms that it is encountered with. So one is the current that is reaching onto the collector side, that is the large chunk of current, that is IC, that is ICNE, IC. Here is one loss mechanism, and the loss is due to what?
Recombination.
Recombination at the base, that is alpha T, recombination at base. And another loss is that we have already discussed. Another loss is nothing
Backward
but,
injection.
sorry, forward injection. This is forward injection. Sorry, this is backward injection. Yes, that is alpha. That is loss 2, and this is loss 1. So gamma and alpha T basically make up the loss, make up for the loss. And after this two losses are there in these two regions, we finally make up getting this large chunk of current, that is IC, that will reach to the collector region. So again, I am just drawing this thing as a whole, as because this whole condition will apply when we will give a forward bias to this region in Pn, and will give a reverse bias to this region. So this is IC in this direction, this is IE, in this direction, and this is IB. With the voltage polarity, it can be seen here. Now, if we can apply KCL, then what is that? The total number of currents that is entering into the device is equal to the total current that is leaving the device. So IE is nothing but, IE which is leaving the device is nothing but IB plus IC. IE is equal to IB plus IC. Here IE minus IC is equal to IB. Now we have IE is equal to alpha T or alpha, or IC by alpha, this one, putting the value from the previous thing that we have already discussed. divided by IC, that is equal to IB. From here we have IC 1 minus alpha by minus 1 divided by is equal to alpha, and here what we have IC is equal to alpha by 1 minus alpha dot IB, isn't that? Now this has got a particular name, that is beta. So beta, this is beta IB. So IC is nothing but beta IB. So we have some problems with IC, IB, and beta. Let us stop right here at this position. We have lab on at 2:30, and the thing is that now we have arrived at a condition where we can actually see that there are various conditions that basically dictate the collector current, and the collector current is mainly guided by the two loss mechanisms, and that those two loss mechanisms are nothing but one is the base transport factor and another is one is the recombination at the that is the emitter injection efficiency. So we will continue BGT in the next class. Let us stop here. Any question from here? কোনো জায়গা যেটা বুঝতে পারেনি ঝট করে বলো. We have to sign it off. Yes, any query?
Ma'am.
Yes. Yes, any query from your part? নেই তো?
No, ma'am, নেই।
ওকে, মানে সবাই খুব ভালো বুঝেছো তাই তো? সবাই খুব ভালো বুঝেছো, তাহলে নেক্সট দিন পটাপট অঙ্ক করতে দেবো। দেখো এবার নেক্সট ট্রান্সপোর্ট আমরা যেগুলো পড়বো সেগুলো কিন্তু জাস্ট দ্য অ্যাপ্লিকেশন অফ হোয়াট উই হ্যাভ the understanding the basic device physics. These are the applications of these things. So before I think that all of you must, who are sincere enough, you have started reading the basic device physics, because without that you could not understand the devices that we are going to introduce one after another in due course of courses of time. So please do that, read that one, make room for questions and all that. I think some of you still are lacking the basic fundamental, that is still we are far away from that portions. So make clear with those things before we reach to the end. Okay, so after that we will have some, and maybe we will be meeting at 2:40. Okay, 2:40 I will just I am there in the meet link, I am not signing it off. You can sign it off and you will be joined, so in this link only.